This video, we're going to solve polynomial and rational inequalities. I'm going to use a number line technique to help us do that. Remember that when you're going to solve these inequalities, you're going to want one side of the inequality to be equal to 0. It's not written that way already. That's going to be our first part of the process here to get everything on one side and 0 on the other side. Then we're going to factor completely to be able to solve our polynomial or rational inequality. So our first polynomial inequality is already factored for us and has 0 on the opposite side of the equation. It's a strictly greater than sign. So the zeros of this would be at -6 and -2. It's not allowed to be equal to those numbers, so I'm going to put open circles there. Then I'm going to use some test points. Anything greater than a -2 would have a positive times a positive would be positive. Anything between -6 and 2 is going to be a positive times a negative, would be negative. And anything less than a -6 is going to be a negative times a negative is going to be a positive. The things that are greater than 0 are the positive values. So my solution set to this in interval notation is -∞ to -6, not included, union -2, not included, to +∞. Our next problem, x plus 2 times x minus 4 is less than or equal to 0. We have zeros at -2 and 4, which are included this time because of that line underneath the inequality symbol that means or equal to. When we stick in a number greater than 4, we have a positive sign. Then when we stick in something between -2 and 4, we get negatives. And when we stick in something less than -2, we'll get positive. We want things that are less than 0, which is negative. So our solution set this time is -2 included to 4 included. Now let's try x squared minus 5x greater than or equal to 0. This one's not factored yet, so we're going to factor it completely. We have zeros at 0 and 5 that are included. When we have a number greater than 5, it's going to be positive. This is going to be negative, and this is going to be positive. We want the positive portions since we're dealing with a greater than inequality. And our answers are -∞ to 0 included, union 5 to infinity. Now let's try x squared plus 6x greater than or equal to 0. X times x plus 6 greater than or equal to 0. We'll have zeros at -6 and 0. They'll be included. When I have a number greater than 0, this is positive. Between -6 and 0 is negative. And then that section is positive. We want greater than, so we're going to shade the positive areas. We get a solution set of -∞ to -6 included, union 0 included to infinity. I'm going to skip down a ways now and talk about another type of problem that we're going to have. 90 times x squared minus 1 is greater than 19x. Notice that the right-hand side is not equal to 0 yet. I'm going to multiply 90x squared minus 90. And I'm going to subtract from both sides. Now I'm going to factor. So factors of 90 are probably 9 and 10. Factors of 90 are also probably 9 and 10. Negative 100 plus 81 is going to give me a negative 19. 10 ninths and negative 9 tenths. Neither can be equal to 0. We can't be equal to either because we're not allowed to be equal to 0. My sign pattern is like so, and we want the parts that are going to be positive. Let me look for another example here. Okay. Let's go ahead and look at one where we have a polynomial that we need to factor. Like so. Plus and minus. Factors of 144 we know are 12 and 12, but that's not going to work. So maybe we want to look at some other ways to factor it. Maybe 4 and 36 will work. So negative 36 and a positive 4. X squared plus 4 won't break down anymore. So this is x plus 6 and x minus 6. My only zeros are going to come from negative 6 and 6. Not interested in that one because it gives complex solutions. 0. This factor is always going to be positive. So over here, when I pick a number greater than 6, it's a positive times a positive times a positive is positive. When I come across 6, this one's going to change sign. So that's going to be positive, positive, negative. And when I cross negative 6, this one's going to change sign. Positive, negative, negative is going to be positive. The things that will be greater than 0 will be like so. Let's try this one before we move on to some rational inequalities. This is a difference of cubes. This one's not going to give me any zeros. The only zero is going to come from 3. It's allowed to be equal to 3 because of the or equal to sign here. Whenever I stick in a number bigger than 3, this will be positive and this will also be positive. When I stick in a number less than 3, this will be negative and this will be positive. So they multiply to give me a negative. And I want numbers greater than or equal to 0. So my solution set is going to be from 3 included to infinity. Rational inequalities are a little bit more interesting, but they follow the same concept of me being concerned with the signs like I was just doing there. They follow very similar sign rules because remember, multiplication and division of integers all have to do with how many negative signs I have. If I have an even number of negatives, it's positive. An odd number of negatives, it's negative. What we're going to watch out here for, though, is that even when I have something where it is, let's say, x minus 4, x plus 4 over x less than or equal to 0, I have to start off by eliminating the numbers that are not in my domain, like 0, before I worry about my zeros that are 4 and negative 4. These can be included to give me 0, but I'm never, ever, ever allowed to divide by 0. So there must be an open circle there. Now I'm going to pick a number that's larger than 4, which is going to make all my factors positive. Then I'm going to cross over this boundary because it's an odd multiplicity, it will change sign. And cross over this boundary, and because it's an odd multiplicity, it's going to change sign. I'm going to cross over this boundary, and because it's an odd multiplicity, it's going to change sign. I want the things that are less than or equal to 0. So that's going to be negative infinity to negative 4 included, union 0 to 4. 0 is not included, 4 is included. Let's try something where the right-hand side is not equal to 0 yet. Something like this. So we're going to make a common denominator. We're going to factor. I'm going to eliminate what makes my denominator 0. And then I've got, these are not included because there's no or equal to there for this problem. I stick in a number bigger than 7, this is going to be positive. And because all of these are odd multiplicities, I'm going to change sign every time I cross a boundary. Less than 0. It's going to be like that. Negative infinity to 0, union 4 to 7. I'm going to look for one now that has an even multiplicity on one of the factors, like number 32. Just to show you what I'm talking about how the multiplicity plays into things. Actually, let's do number 31. X minus 2 squared over x squared minus 36 greater than 0. So that's x minus 2 quantity squared, x plus 6 times x minus 6 greater than 0. We're definitely going to have the function undefined at -6 and 6. And we're not going to be allowed to have the function equal to 2 either because it's not allowed to be equal to 0. Now watch the signs here. When I cross this, this is going to be positive over here on this side when all the numbers are positive. And I cross this boundary, x minus 6 gives me the 0 of 6 here. It's an odd multiplicity, so it's going to change sign. When I cross the boundary here, because this is an even multiplicity, it's not going to change sign. You can check that out. Stick in a 1, for instance, a -1 squared. That's going to be a positive number up here. And then you're going to have a positive times a negative. is a negative in the denominator. If I had put in a number like 3 in the top, 1 squared would be 1, and it would be positive times negative. That's still negative. When I cross this boundary here, since that's an odd multiplicity, it's going to change sign. So it's not always alternating every time. It changes sign when there's an odd multiplicity, and it doesn't change sign when there's an even multiplicity. It's one of the reasons we talked about multiplicities in an earlier video before this. So you can go back and watch that video if you would like to. Oops, that was too far, too fast. Let's go ahead and do one that has fractions on both sides, like number 35. You need to bring everything to the left-hand side. Then we need to make a common denominator. Not allowed to multiply by that variable on both sides to try and clear the fractions, because we don't know whether that expression would be positive or negative. It depends on the value of x. So we don't know whether we would maintain the direction of the inequality sign or change it. So we're going to go ahead and make this 15x plus 15 minus 12x plus 48 over x minus 4 times x plus 1 greater than 0. It's going to make this a 3x plus 63 over x minus 4, x plus 1. There's a common factor of 3 in the top. Set up our number line here, the negative 21, a negative 1, and a positive 4. All of them are going to be open circles. All of them are odd multiplicities. We want the ones that are greater than. So our solution to this problem is going to be negative 21 to negative 1, union 4 to infinity. I think that's enough of the different types of problems that you're going to see with polynomial and rational inequalities. These are going to be important when you get into calculus. You want to talk about where the function is increasing, decreasing, concave up or concave down. For right now, in pre-calculus, you will use these to determine where the function is above or below the x-axis. That's what you're going to be asking with these. So when you're graphing your polynomial or your rational functions, you can use these inequalities to help you figure out if the graph is above or below the x-axis in a certain region. All right. See you for our next video when we come back and talk about something different. We're going to talk about inverse functions, and that will lead into a discussion of exponential and logarithmic functions, which are inverses of one another.